If our sun suddenly turned into a magnetar, we'd all be cooked, and pretty quickly. Magnetars pack about 1.5 times the mass of our sun into an incredibly small space. They're tiny and super dense remnants of ancient stars that have gone supernova, and they have an unimaginably powerful magnetic field. Yeah, this little star would kill everything on Earth, including you. In this video, we'll show you how life would change or end if we replaced our star with some of the most extreme objects in the universe. Some of these, surprisingly, could be better for us than the sun. But before we get into it, we want to hear what object you would want to replace the sun with. Why not tell us your pick in the comments below? Okay, now let's test them all out, starting with a red giant.
Oh my god! Oh dear! Are you filming? Yes, I'm filming!
The bad news is that the sun really will swell up into this kind of red and hot exploding star, and it would swallow Mercury, Venus, and even Earth. The good news is that it'll take 5 billion years to get there, give or take. You see, our sun is what scientists call a G-type yellow dwarf. It's a main sequence star. It runs on fusing hydrogen into helium, but its clock is ticking. The sun formed 4.6 billion years ago. A star like this only has a lifespan of 10 billion years. Only. And when it dies, it goes out with a boom. A red giant kind of boom. But we're not going to be around in 5 billion years to witness the death of the sun. So how about we speed things up and replace our star with the red giant now? Well, because that would mean instant death for you. Because as I mentioned earlier, this red giant would swallow Earth whole. You wouldn't even get a chance to enjoy the view. Immediately, Mercury, Venus, and Earth would be obliterated. And not because this red giant would be so scorching hot. No. The sun's surface burns at 5,772 Kelvin. That's about 5,500 degrees Celsius, or 10,000 degrees Fahrenheit. Red giants burn cooler, mostly because at this point in a star's life, it's burned up all of its hydrogen. This star's surface temperature would be around 3,000 Kelvin. That's just 2,700 Celsius or 4,900 Fahrenheit. But red giants got their name for a good reason. A giant reason, I should say. Yeah, this ball of helium would be 200 times larger than the sun. And it would be anywhere from 1,000 to 5,000 times more luminous. Even if you could look at it just for a second, you'd lose your eyesight. At first, everything would become very bright and orange. The sky would look like it's on fire. You'd be blasted by the most intense heat wave as temperatures on Earth rose by hundreds of degrees. Next, the oceans would boil and disappear. Within minutes, Earth itself would get dragged into the red giant's outer atmosphere. Our planet's crust would melt. All life would burn. The red giant would reach Earth's orbit, blind us, broil us, and then there would be no more Earth left. Gone. Even Mars would get a violent blast of heat. Its carbon dioxide ice caps and permafrost would vaporize instantly, creating a thin atmosphere of gas and steam. It sounds like great news for Mars, but it's not really. Strong solar winds and intense radiation from the expanding red giant would strip away that thin atmosphere in no time. The Martian surface would be hotter than the melting point of lead. All the sand and rock on its surface would melt into a glassy blob. For a short time, Mars would glow like a red-hot coal, but then it would just end up as a dead rock. Other planets further away would be affected too, because the red giant would gradually lose its mass. Its gravitational hold on Jupiter, Saturn, and the other surviving planets would weaken. Any planets that weren't burnt to a crisp would slowly drift away out into outer space. Okay, that was a pretty violent end for Earth. On a scale of how spectacularly we die, I'd rate it a 9 out of 10, taking a point away for not being able to enjoy the view, even briefly. Okay, next, let's go a little easier on Earth and replace the sun with a red dwarf star. Red dwarf stars aren't the same as red giants. These are the most common types of stars in the universe. Most of the exoplanets we find out there in space are orbiting this kind of star. Now, the sun will never become a red dwarf, not even in billions of years, but if it did, well, it wouldn't be so bad. First, it would become really small and dim. Red dwarfs are much cooler than our yellow dwarf sun. Their average surface temperature is about 3,300 Kelvin. That's 3,000 degrees Celsius, 5,500 degrees Fahrenheit. Replacing the sun with this kind of star would cause the skies on Earth to look dark and faintly colored. It'd be like a deep dusk or dawn, even at noon, with a small reddish-orange dot. It's so dim that you could look directly at the red dwarf for a brief moment without any eye damage. But because this new sun would be so dim, temperatures on Earth would start to drop by a lot. Within 1 week, the global surface temperature would fall below minus 18 degrees Celsius. That's 0 Fahrenheit. Within a year, Earth would be about minus 73 degrees Celsius, minus 100 Fahrenheit. The effect of this cooling would take time, but eventually, everything would freeze. The only place left that would still have liquid water would be deep under the oceans. At first, you'd see intense storms and heavy snowfalls, but eventually, the water cycle would stop. There'd be no rain, no snow, no wind, and there wouldn't be enough solar energy for plants to perform photosynthesis. Plants would be the first thing to die out, and soon after, the entire food chain would collapse. In this climate, only the hardiest microbes would have a chance. Some microorganisms deep in the Earth's crust or around hydrothermal vents in the ocean could survive indefinitely, but on the frozen surface, all forms of life would be wiped out. Over the years, the cold would become more intense, and even the near-surface bacteria would go dormant or die. Earth would become a sterile, ice-bound rock. Now, it wouldn't be all that bad because at least you wouldn't die instantly. You might have a chance to leave the planet and travel someplace more pleasant. That is, unless Earth itself took off out of its orbit. Here's the deal with red dwarfs. They're way less massive than the sun, so their gravitational pull in the solar system wouldn't be strong enough to keep all the planets in place. Earth might break off and become a rogue traveler in deep space, getting even colder, darker, and more inhospitable for life. And that would happen fast. Gravity travels at the speed of light, so Earth could start feeling the change as soon as 8 minutes after the sun turned into a red dwarf. Our planet wouldn't immediately shoot off into deep space. No, it would gradually begin drifting away, and then eventually we'd leave the solar system. But at least you'd still have a little time before your imminent death. So, a red dwarf filling in for the sun? Well, I give that a 4 out of 10. Okay, let's move on to something that's not very common in the universe. Turn our sun into a blue star. A blue star. Blue stars might look cold, but they actually run extremely hot. These O-type or B-type main sequence stars are the hottest and most massive stars in the universe. You don't see them very often. O-type blue stars make up only about 0.00003% of stars in our Milky Way galaxy. And our sun physically could never gain enough mass to become a blue star, but if it did, it would look interesting. Daytime on Earth would have an intense, almost stark blue-white glare. The sky would take on a deeper blue or even a violet tint. This blue star would be a lot brighter than the sun. Do not look at it with the naked eye. This bluish light would be overwhelming. Oh, and did I mention it would shower you in extreme levels of radiation? Yeah, Blue stars are monstrous. The blue supergiant star, Rigel, emits 60,000 times as much energy as our sun. And some blue stars out there, like Eta Carinae, put out 1 million times the energy of the sun. Even if our new blue sun were a less extreme blue star, Earth would suddenly be receiving hundreds to thousands of times more radiation. If you were exposed to this blue sun just for a few seconds, you'd get an instant sunburn from all the UV radiation. And just as quickly, the Earth's surface would start to heat up. Instead of a global average of 15 degrees Celsius, 60 Fahrenheit, you'd be dealing with temperatures of several hundreds to thousands of degrees. In a matter of days or weeks, Earth would heat up to the point where rocks and metals melt. The oceans would boil away and all life would incinerate. That would be the end of Earth. The good news is that if this blue star had the same mass as the sun, well, nothing else would change in the solar system. Would Mars become a little more habitable? No, but it would become less deadly than Earth for a short time. It would get warmer on the red planet, but the amount of radiation the blue star would bathe Mars in, well, let's just say we wouldn't want to be building habitats there. Blue star? I give it a 5 out of 10. Deadly, but not as dramatic as the red giant. You know, Chase has been dying to go to his star for his next mission, but we're not exactly sure where to send him. What star do you think we should send Chase to? Well, tell us in the comments below. Now, let's see if we can crank it up a notch and turn our sun into a neutron star. Neutron stars are epic. They're born out of a massive explosion called a supernova. It's one of the most violent and energetic events in the universe. The whole blast only lasts about 1 second, but in that second, a star releases 99% of its energy. This mega event can outshine the galaxy for weeks. Of course, there's no way you are surviving this kind of blast, and our sun is way too small to burst into a supernova anyway, so let's skip the initial blast and replace the sun with a neutron star in a more calm way, like this. Within 8 minutes of the last drop of sunlight, the sky would fade to black and stars would appear, even if it were daytime. You wouldn't see the moon or the planets because you can only see them by reflected sunlight. You wouldn't even see the neutron star in the sky. It would be practically invisible to your human eyes. From now on, it's forever night on Earth. And you probably know where this is going. Without sunlight, there'd be no photosynthesis, no plants, no life. Earth would gradually become a frozen rock. But it would be bathed in a different kind of solar energy. Neutron stars are unimaginably energetic, especially if they're pulsars. If this neutron star had a spinning core, that would make its magnetic field stronger. It would become a rotating, magnetized neutron star, or a pulsar. And now you'd be dealing with periodic blasts of intense, high-energy radiation. From Earth, these bursts would appear as an aurora-like glowing in the sky. With time, the effects of this radiation would become more intense and cause electronic disruptions, skin burns, and radiation sickness. Life on the surface would be wiped out from two sides, freezing from a lack of solar heating and being irradiated by the neutron star's high energy. Earth would freeze and fry at the same time. But once you zoom out a bit, things would be business as usual. The neutron star would have about the same mass as the sun, so it wouldn't disrupt the solar system's delicate orbital order. Neutron stars, way too radioactive. They sound epic. I wouldn't want to live close to one, so I'm gonna give it 7 out of 10 on the destruction scale. Okay, next up, let's replace the sun with a magnetar. Magnetars are extreme, maybe more extreme than neutron stars. Well, technically, magnetars are neutron stars, just with a little sprinkle of magnetism. And just like neutron stars, Magnetars are small, about 20 kilometers or 12 miles across, but their magnetic fields are trillions of times stronger than Earth's. Then here's a bummer. If you expect this kind of view, well, don't, because if the sun suddenly turned into a magnetar, you wouldn't see anything in the sky. That's because magnetars emit most of their energy in X-rays and gamma rays, not in any visible light you can see. Once again, just like with Jimmy Neutron star, it would be all night and no moon. And here's another interesting thing about magnetars. These things are burning hot. I mean, all these stars are, but a magnetar's surface temperature is millions of degrees. But on Earth, you wouldn't get all that much heat from one. Again, they radiate their energy as X-rays and gamma rays, not as visible or infrared light that would warm Earth's surface. Plus, a magnetar's surface area is really tiny, so just like in the case of a neutron star, Earth would be blasted by deadly radiation, and it would freeze because of a lack of warming light. But unlike the neutron star, a magnetar would instantly fry our satellites and power grids. Its radiation is way deadlier, and it would also completely disrupt the Earth's magnetic field. A magnetar's intense magnetic field and gamma ray flares would violently compress the Earth's magnetosphere. And you want the Earth to have a stable magnetosphere because that's what holds the atmosphere in place and protects you and me from space radiation. Not only would Earth become technologically blind and deaf, it would also be showered in so much radiation you might turn into the Hulk. Yeah, brother. Ooh. No, not that one. The one who turns green. Yeah, well, that really only works in the Marvel universe. But hey, at least you'd get the view. There'd be incredible auroras in the sky. I was really looking forward to a magnetar. Epic! That's an 8 out of 10. Next up, the scariest and hungriest object in the universe. The black hole. Yeah, remember how I said that some of these extreme objects might be better for Earth than the Sun? Well, scratch that. Nothing is better than the Sun. And a black hole is definitely much worse. To be a little more gentle to our planet, well, let's say that this new black hole in the center of our solar system had the exact same mass as the Sun. Because a supermassive black hole, yeah, that one would just suck you in and not spit you out. But a nice sun-massed black hole wouldn't even disrupt the Earth's orbit. This epic view from Earth. Wait, that's not right. If our sun was turned into a black hole, you wouldn't see a fiery disk in the sky anymore. There'd just be, well, just nothing. That's because a black hole with the same mass as our sun would only be about 6 kilometers, 3.5 miles wide. Bummer, I know. But grab a telescope, you'll see that the space where the sun used to be isn't completely empty. You see, black holes bend light around them, and without the sun's blinding glare, you'd start noticing the stars in the background being smeared into arcs. This effect is called gravitational lensing, and it's really the only way you could see the black hole at all. If some distant star lined up just behind the black hole, you'd see something called an Einstein ring, a perfect circle of starlight wrapped around a pitch black shadow. But like I say, you'd need a telescope to see it. Now, as far as life on Earth goes, well, you and everyone around you would soon freeze to death. Maybe not immediately or overnight, because Earth would still have some internal heat. But after a few years, almost everything at or near the surface will be frozen solid. After millions of years, Earth's equilibrium temperature would get as cold as minus 240 degrees Celsius. That's around 35 Kelvin or minus 400 degrees Fahrenheit. And that's a complete freeze-over. Nothing would survive here. But on the bright side, at least you didn't get sucked into a black hole, so that's a 6 out of 10 for me. Black holes are dangerous and very strange. Even a nanosecond in one would stretch you out into a state of human spaghetti. Now, the closest one of these monstrosities is just 1,500 light years away, and I wouldn't recommend jumping into it. If you did, It'd be a cosmic nightmare, or a trip to a parallel universe. Things are getting hotter and hotter here on Earth. It's getting out of control. So let's try something new. We're going to take all of Earth's water and pour it on the sun. I'm talking every single drop. Maybe that'll cool things down a bit. But is this even possible? Why is getting to the sun so difficult? And once we drench the sun, what would happen to life on Earth? This is What If, and here's what would happen if we poured all of Earth's water on the sun. Okay, before we go about gathering all the water on Earth, shipping it to the sun, and pouring it on top of our burning star, we need to look at the magnitude of what we're up against. The sun is the most massive thing in our solar system, a big ball of burning hydrogen, 1.3 million times the size of Earth. It's so hot that it's like 15 billion atom bombs exploding every second. It's got a temperature of 5,600 degrees Celsius. Okay, it's not actually a big ball of burning hydrogen. About 70% of the sun is hydrogen, and then 28% is helium. The other 2% is comprised of carbon, nitrogen, oxygen, and other elements. The sun is super far away. It's about 400 times further away than the moon. That's about 150 million kilometers away. For reference, the circumference of the Earth is just 40,000 kilometers, so talk about being a long road trip, or space trip. And it's no ordinary fire that burns inside the sun. The huge amounts of heat and light that are given off come from nuclear fusion reactions. We'll come back to that later, but this is the fire that we're tasked to put out. It's not just that the sun is hot, it's like a ticking time bomb. The sun is getting hotter and hotter every second. So maybe you're wondering, is that what's causing global warming? Well, no, that's still being caused by us humans and the carbon dioxide we release into the atmosphere. Sure, the sun is getting hotter, but only about 1 degree every 100 million years. Okay, let's be real. Things are getting a lot steamier on our blue marble, so maybe instead of getting rid of fossil fuels, we can just turn the sun's thermostat down. And this is how you're going to do it, by taking all the water on Earth and pouring it on top of the sun. Kind of like the Ice Bucket Challenge, but more of a cosmic scale. Maybe that'll make the sun a little cooler. And if that doesn't work out, we've got one more trick up our sleeve. I'll tell you about that later. The first thing we need to figure out is how much water there is on Earth. 71% of the planet's surface is covered in water, which is about 1.3 billion cubic kilometers worth. That's 554 trillion Olympic-sized swimming pools. Safe to say, that's a lot of water. Okay, so now you've got a handle on some of the awesome power of the sun and the enormous water resources on Earth. It's time to get started. Why don't we test our theory with something a little bit smaller? Instead of all of Earth's water, let's start by shipping just a single glass, about 250 milliliters, 8 ounces. This should be a lot more doable and less resource intensive. Before we take off, the first thing we need to figure out is our spacecraft. For this mission, we're going to be using the Parker Solar Probe. This ship is about the size of a horse and weighs 555 kilograms. Sure, adding a small glass of water to the ship won't hurt. In 2018, the Parker Solar Probe traveled the closest a ship has ever been near the sun. And for this mission, we're getting real up close and personal. Well, sort of. At its closest, the ship will still be 6.2 million kilometers from the sun. Wait a minute, NASA, can't you get any closer? No, NASA says it's super hard getting to the sun. And it takes 55 times more energy to get to the sun than Mars. I'll tell you why in a second. As the probe takes off, the weirdest thing will happen. It'll shoot backward instead of forward. This is because the Earth is traveling very fast around the sun at 107,000 kilometers per hour. To shoot something to the sun, you need to account for the Earth's momentum. So instead of launching forward, it launches backward and ends up going sideways until it reaches our star. Simplest way to think about it is kind of like when you take the wind into account when you're throwing a frisbee. Not that I'm any good at that. Okay, since the probe will take a while to get to the sun, let's fast forward a few years to where the probe is now in place, as close as it can get to the sun. And a robotic arm comes out, turns the water upside down, right on top of the sun. Well, in milliseconds, with a brief hissing sound, the water just turns into vapor. Absolutely no change to the sun. Well, actually, if we get a measurement from the Parker probe, it seems the sun is a microscopic bit heavier. Heavier? But the sun was going to get doused and get lighter. Okay, well, maybe the probe got the measurements wrong. Okay, time for your second attempt. Only this time, you're going to get serious. No messing around with a wee glass of water. Admit it, that got us absolutely nowhere. This time, we're taking an entire lake from Earth and dumping it on the sun. Let's take Lake Superior. This lake is massive. In terms of surface area, it's the largest lake in the world. In terms of volume of water, it's the third largest. If you took all the water from Lake Superior and poured it over North and South America, we'd all be standing in 30 centimeters of water, 1 foot of water. So how are we going to drain this lake? Well, first, we've got to assume that we've got permission from the federal governments of Canada and the United States. After that's done, we execute. We dig a drainage channel and connect it to a pipeline that'll take it all the way to our starships located at SpaceX headquarters in Texas. Yeah, you're going to need a bunch of those to launch all this water at the sun. But how long does it take to construct a pipeline? Well, it could take anywhere from 5 to 10 years. We don't have time for that. Maybe we can borrow an existing oil and gas pipeline, a pipeline that carries 3 million barrels of oil a day. We could repurpose it to carry the water. Well, let's see, that would still take about 70,000 years to transport all the water. That's a problem. Okay, the pipeline method, way too slow. We need a better idea. What if you used a really powerful pump instead? The most powerful pump on Earth, which you'll import from the Netherlands, the Nijhuis pump. It can pump 1,200 cubic meters a second. At that rate, it would pump 1 cubic kilometer in about 10 days. Then you'll pump the water into huge tanker trucks. The biggest are the large-scale construction tankers. Those trucks carry 227,000 liters of water at a time. Now we got the right idea. So, if you installed this pump on Lake Superior, how long would it take to get all the water out? Well, Lake Superior has 12,100 cubic kilometers of water. Pumping that would take 121,000 days, 320 years. Still a lot of time, but better than 70,000 years, I guess. So let's multiply the pumps. Let's use 320 of them and cut the time down to 1 year. That sounds like a plan. Even better, if you're willing to spill some cash, we'll build 960 pumps and get it done in 4 months. And then there's another thing we have to figure out. How much is pumping all this water going to cost us? These pumps have to be constructed inside a pumping station, and the construction can cost $1 billion and takes about 3 years. So building 960 of them? Well, you get the idea. A lot more time and money. And all that construction would definitely mess with the environment and scenery around Lake Superior. You'd probably cause some of the local bird species to go extinct. Getting US approval will be a nightmare, and you'd probably cause an international incident with Canada. But then again, this is a plan to save the world, so hopefully everyone on Earth would get on board. For science. Okay, let's say you do manage to get this done. Somehow then, you'll need to transport the water to the launch site using the huge tanker trucks. How many of those will you need? It's going to be 53 billion tanker trucks for all that water. Yeah, that seems pretty unreasonable and likely impossible. All right, I hate to admit it, but this pump and tanker truck method is going to be a no-go. But you know what? Instead of moving this mass of water from the Canadian border all the way to Texas, why don't we just move the launch site? Launch the water rockets directly from Lake Superior. Building a rocket launch site would take a lot less time and money than moving all this water. We'll pipe the water from the lake right into our starships. That should work, right? If we don't plan on bringing our starships home, they have a payload capacity of 250 metric tons. How many ships would we need to deliver all this water? The answer is, of course, 48 billion of them. Okay, it's going to be tough even to build this many ships, but let's say we did it somehow. Then we'd start launching them from 1,000 rocket sites on a crazy schedule, every 3 seconds, round the clock, for 4 years. But we're going to have to fuel these starships as well. To get to orbit, they use 1,000 tons of methane and 4,000 tons of liquid oxygen. To fuel all these ships, that's 48 trillion tons of methane and 192 trillion tons of oxygen. And we need even more fuel than that to get to the sun. Well, let's just assume that we do it somehow. Our starships are taking off one by one. As the starships get closer to the sun, they're heating up. The temperature in this region is around 500,000 degrees Celsius. The Parker probe was equipped with special heat shield technology, but our starships can't withstand the heat. They start to melt, and all that water, it's become water vapor mist. Darn it, spectacular failure. We were so close. Right, now for a different, outside-the-box strategy. What if we connected a giant hose and aimed it straight at the sun? This is a super advanced mega project that's never been done before, but you're going to do it. This hose has to be 150 million kilometers long, and you're going to make the last 10 million kilometers with special heat-resistant tech so that it doesn't melt. It's not like we haven't learned anything from our previous experiments. It's a little out there, but let's say it works. Okay, Lake Superior is draining into a giant hose. Powered by a massive nuclear reactor, you're shooting all that water from the lake directly into the sun. Since you're doing this from Earth, you'll have to wait to get a reading back from the trusty Parker probe that's circling the sun. It'll report what's going on up there. As the water is hitting the sun, something incredibly strange is happening. The sun is actually burning a little brighter. It's almost as if you threw extra fuel into this fiery giant. What's going on here? Well, to understand, let me tell you a little more about how fire works. We all know what fires are like here on Earth, whether it's a campfire or flame coming from your gas stove, but these fires work differently compared to the sun. What happens in a regular fire is known as chemical combustion. Carbon in the fuel combines with the oxygen to form carbon dioxide. What's needed for these fires to keep burning are 3 things: fuel, usually wood or gas, coal, plus oxygen, and a high temperature. When you throw water onto these everyday fires, 2 things will happen. 1, the water absorbs some of the heat, lowering the temperature, and the second thing that might happen, well, the water might reduce the amount of oxygen that's available to the fire and put the flames out that way. But the sun, its fire is a little bit different. Even though we call our sun fiery, it's not the same fire we see here on Earth. See, the sun's fire comes from fusion reactions. Billions of them are happening every second. Yeah, a little different from your average campfire. So when you throw water on the sun, instead of cooling it down, you end up giving the sun more power. The water vaporizes from the intense heat of the sun and turns into hydrogen and oxygen, which just so happens to be more fuel for the sun, making it burn brighter. As the water from Lake Superior is hitting the sun, it's producing more and more hydrogen for the star to gobble up. Could this make our sun explode? Well, not quite. There's already a huge amount of hydrogen in the sun. This is just a tiny drop in a massive ocean. Okay, we now know that a small amount of water can potentially make our sun stronger, but maybe things would be different if we took every little bit of water on Earth and poured it directly on the sun. That's got to put it out, right? Right, guys? Well, to make this happen, you're going to have to drain the oceans. They make up 97% of Earth's water. And you're not going to bother with starships and tanker trucks or even a hose. You're going to build a portal from the Earth to the sun. Let's fast forward to how we get to this technology and start building. We start at the deepest spot in the ocean, Challenger Deep, 11 kilometers below sea level. It's situated in the Mariana Trench. It's pretty hard to construct anything down there. The water pressure is intense. It's more than 1,000 times the pressure at sea level. So we'll just make a portal that's 10 meters wide. But with a portal this size, it's going to take hundreds of thousands of years to drain the ocean. At this rate, the water level will drop by less than 1 centimeter per day. The problem is that the ocean is just so large and this hole is just too small. Okay, so let's make this hole wider, or dig a few more portals and arrange them at different spots over the sun. Right, now all the water from Earth's oceans is draining out and getting poured over our star. You get a new readout from the Parker probe. What's happening 150 million kilometers away? Not much. So, what is the Parker probe getting this right? All that water you drained out, all of it, vaporized as it got closer to the sun. The extra hydrogen increased the sun's mass. But even now, with all the water from all the oceans on Earth, the sun's mass has increased just a tiny amount. Because even though that was a lot of water, it was only 0.02% of Earth's weight. Think about it, the sun has 330,000 times Earth's mass. So that amount of additional hydrogen, nothing more than a splash of fuel for the sun. Ugh, now you've used up all the water in the oceans for this experiment. Our blue marble is looking pretty brown. What's gonna happen to Earth? Things are now a disaster on our home planet. The oceans are now a mass graveyard. Millions of fish, big and small, from tiny plankton to massive sharks, are all dead. All because you wanted to see if you could douse the sun. Humans are in an absolute state of panic. They're frantically calculating how much water is left in the icebergs and in freshwater lakes. How long can that sustain the planet? Thank heavens you left 3% of the water behind. That's 11 million cubic kilometers, and we humans use about 5,000 cubic kilometers a year for all our activities. But wait a minute, we don't melt icebergs for water, we use groundwater and fresh water. So scratch that 11 million, the fresh water in the lakes is just 93,000 cubic kilometers. That won't even last 20 years. Plus, it's getting super hot. With the oceans dried up, water isn't able to play the important role it does in our climate. There are no ocean currents to carry heat away and spread it across the globe. No place for all our carbon to go. Total disruption of our cycle of rainfall. Forest fires everywhere. With rain cycles disrupted, plants will die out and animals will follow. It's a climate crisis, an ecological crisis, and a water crisis all happening at once. I guess the problem we were trying to solve initially got even worse with our efforts. Temperatures would rise to 67 degrees Celsius. That's 150 degrees Fahrenheit. If humans are to survive this crazy heat, we're gonna have to change our way of life drastically. Hide out in Antarctica or live in underground bunkers. The grim reality would be that without oceans to get a water cycle going and without plants, life on Earth would be over. Still, on the bright side, you did find out that throwing all this ocean water at the sun won't extinguish it. At least that's something. Science, yay. Okay, Earth is a mess, but you're still curious about one thing, and you have one last move you want to try. And now it's so hot that you think it's worth it to get the sun to cool down just a little. What if you threw a ball of water the size of the sun at our sun? What would happen then? I know, that sounds nearly impossible. Where would you get a sun-sized ball of water from anyway? Well, I'm not sure. There's definitely not that much water, even if we collected all the H2O in our solar system, because the sun has 99.8% of the solar system's mass. But let's assume that somehow we got this massive ball of water together. Before we get to the sun's reaction, let's look at this giant ball of water. It contains about 1 billion times all the water that's currently on Earth. I mean, that was on Earth before you drained it away. Since water is in contact with space, something weird happens on the surface. In the vacuum of space, there's zero pressure, so the water boils, becoming water vapor. But then, because the temperature is so low, the water vapor freezes almost immediately into ice crystals. If you look at this big ball of water in the sky, there'll be a huge vapor cloud around it as this evaporation and freezing happens. A ball of water this big will also exert a huge amount of pressure on its core. Now, As a result of this intense gravitational pressure, it'll begin to collapse in on itself, and as the pressure in the center increases, the temperature will rise. Under high pressure and high temperature, water molecules in the core might start moving very fast and breaking apart into hydrogen and oxygen molecules. As the hydrogens slam together, they fuse to form helium, releasing energy in the process, and the release of energy further increases the temperature and speeds up the fusion process. Finally, this giant water ball itself becomes a sun, powered by nuclear fusion in its core. Great, I always wanted to have two suns. But another thing might happen. The pressure inside the water ball, though very high, might not be sufficient to start the fusion process, so the ball could become a brown dwarf, which is a failed star. What would happen to our sun? Well, if this giant water ball were right next to our sun, then it may have finally met its match. This water ball would have a mass much greater than the sun, because it's the same size but made of water, and water is much denser than hydrogen. The sun will spiral into this huge water twin and get stretched out in the process. This stretching out of the sun could disrupt the core where all the hydrogen fusion takes place. If the pressure drops, this could slow the fusion process down for a while, but as the two suns come together, it could speed back up, creating an even stronger and hotter sun. Darn it, so is it impossible to disrupt the sun? Well, there's one more thing to try. This is that last trick up your sleeve. It would be to somehow break the sun apart. Instead of just placing them side by side, what if the water sun and our sun met in a massive head-on collision? If that were to happen, just like in planetary collisions, the two suns would split into smaller pieces for a while. A huge vapor cloud would form with smaller but still very big clouds of hydrogen and water. The high pressure at the center of the sun would be disrupted, which would stop the fusion process. Then the pieces would condense again, potentially creating an even bigger sun. When the water sun and our sun crash together, coming apart and rejoining, does Earth get spared the apocalypse? No. Sorry, if anything, the introduction of another giant mass at the center of our solar system would alter the entire gravitational field. The orbits of all the planets would be disrupted, not just in our solar system, but beyond. Sorry, Proxima Centauri, your orbit will never be the same again. Earth, already drained of its oceans, dry, hot, devoid of plants and animals, gets one last kick. We're pushed out of our orbit. That, for sure, would be the end of life on Earth. So, no, you can't eliminate the sun with water.
Imagine you were able to shrink the sun to the size of a basketball. At that point, the Earth would be reduced to the size of a sesame seed. That's how massive our star is. But what if this fiery ball of gas and plasma wasn't the biggest thing in our solar system? Would our planet still orbit the sun? Or would the sun rotate around the massive Earth? What would happen to our planetary neighbors? This is What If, and here's what would happen if the sun was smaller than the Earth. It would take the equivalent of 1.3 million Earths to fill up the volume of the sun. It's so big that it makes up over 99% of the mass of our entire solar system. It only looks small from Earth because it's 150 million kilometers away. If, hypothetically, the sun was smaller than the Earth would be uninhabitable, and the sun, well, this massive star may no longer be a star. In the universe, size matters, and so does distance. It just so happens that the Earth is close enough to the sun that it doesn't freeze over like Mars. It's also far enough away that it doesn't get scorched like Venus. We're fortunate to be in the sun's habitable zone. This means that the size of our planet, the size of the sun, and the distance between the two of us is what's made it possible for life to evolve here on Earth. What would happen if the sun was smaller than our planet? A star's mass determines its color and temperature. Bigger stars are hotter and bluer, while smaller ones are cooler and redder. The sun is a white star, not as big as a supergiant, and not as small as a red dwarf star. You might think that by making it smaller in size, it would just turn into a red dwarf with a smaller habitable zone, but that's not the case. By definition, a star, whether it's a supergiant or a red dwarf, is only a star when there's thermonuclear fusion in its core. How small can stars get? Well, we haven't measured too many red dwarfs at this point, but the smallest one we came across has a mass of 10 Earths. That's very close to the theoretically necessary size of a star to sustain that fusion. Anything smaller than 10 Earths wouldn't be a star anymore, but rather a cold and dark stellar remnant. If, for any reason, the Sun shrank smaller than the Earth, this shrunken Sun wouldn't have the mass to create fusion and would burn out completely. Our solar system would lose its only star. Since the Sun is the source of gravity that keeps us all in orbit, all planets, the Earth included, would float away into space in search of another anchor. That's no happy ending for life on Earth. Let's try this again. This time, let's make the Earth bigger than the Sun, while the Sun's size remains the same. Earth's mass would be at least 333,000 times bigger than it is now. A planet that big would generate enough heat and pressure in its core to become a star itself. Of course, there would be no life left on this hot star, but here's a cool thing. Our solar system would have not just one, but two suns. It would become a binary star system, with two stars orbiting around each other and planets circling them both.
In 5 billion years, we're going to have a hefty problem on our hands. Well, only if we're still living on Earth at this point. Our sun will be on the brink of collapse. If we don't find a way to give it all the fuel it needs, well, we're toast. How could Jupiter help us refuel the sun? What other stars have consumed gas giants? And what would life be like without Jupiter? This is What If, and here's what would happen if we refueled the sun with Jupiter. The sun's delicate balance of hydrogen and helium keeps us alive and well. Although you might think there's an infinite ball of energy up there, I hate to break it to you, but the sun's not sticking around forever. In order to keep it going, our sun needs a consistent source of hydrogen. At its core, the sun's hydrogen is converted to helium in the process of nuclear fusion. This fusion reaction is exothermic, meaning it gives off more energy than it consumes. This energy is released as gamma radiation, which provides enough of an outward push of gravity to keep the sun from imploding. So, how exactly can Jupiter help with all this? Well, about 90% of Jupiter's atmosphere is made of hydrogen. This makes it one big ball of fuel, even though it's only 0.01% the mass of the sun. Astronomers have located a sun similar to ours that has been eating a Jupiter-like gas giant, called WASP-12b. Good one, science. I hate wasps too. WASP-12b's atmosphere is being sucked up by its star, forming a hot ring of gas around it. As its atmosphere is pulled outward, this is making the planet puff up to 6 times the size of Jupiter. Our sun gobbles up hydrogen at a rate of 620 million metric tons per second. With 4 gas giants in our solar system, we could keep the sun sizzling for another 87 million years. With Jupiter being the biggest, we'd probably want to start there. In order to pull this off, we'd need to set up Jupiter like WASP-12b, close enough to the sun to deliver a constant influx of hydrogen from its atmosphere. It would have to be just enough hydrogen so that no mass is added or lost from the sun. In other words, like a healthy diet and exercise with an occasional cheat day. But couldn't we just smash Jupiter into the sun? That sounds like more fun to me. Well, this would make for some good fireworks, but this would increase the sun's mass too quickly,
causing it to burn hot enough to turn global warming into global roasting. The key is to keep the sun's mass stable so its fusion remains consistent at its core. Even if we managed to nudge Jupiter close enough to the sun, that could lead to a whole slew of other problems. Because without Jupiter's stable gravitational pull, all of our planetary orbits, including Earth's, would be thrown off course. And we'd lose our precious shield against deadly asteroids and comets. So, realistically, we'd probably have to suck it up and move somewhere else. Who knows? Maybe there's a really nice Earth-like exoplanet out there for us to settle.
Billions of years in the future, the sun will begin to die. And this is what our planet would look like. But what if we turn things up a notch or two? Let's upgrade our star from yellow to blue. How different would the world look? Could your body handle the increased heat? Or would all life on Earth die? This is What If. And here's what would happen if the sun was a blue star. Like any visible light, sunlight contains all the colors of the rainbow. But how we see a star, or any planet, depends on how hot the star is. The coolest stars in the universe have temperatures of about 1750 degrees and emit more red light, while the hottest stars have temperatures over 40,000 degrees and look bluer. Our sun has a surface temperature of 6,000 degrees, so it emits almost equal amounts of blue and red wavelengths. If you could see the sun from space, it would appear whitish. Hang on a second, the sun isn't yellow? Yeah, that's right. The sun only appears yellow to you because of Earth's nitrogen-rich atmosphere. Red light and yellow light have longer wavelengths and can reach your eyes easier. Blue light has a shorter wavelength and scatters more, giving the sky its blue color. But if our sun was a blue star, you'd never get to see a spectacular orange sunset again. Oh, and also you'd get fried instantly. Now, before making our sun blue, let's take a look at a couple of bright blue stars that we know of. On the cooler end of the blue star spectrum is Rigel, the brightest in the Orion constellation. Its surface temperature is about 11,000 degrees. While it's almost twice as hot as our sun, Rigel emits at least 40,000 times more energy. And Rigel's diameter is 79 times larger than our star. If our sun was that large, it would swallow Mercury, and temperatures on Earth would increase immensely. But why stop there? You could turn the dial up even further. If we imagine our sun on the higher end of the blue star spectrum, it could be like Eta Carinae. With surface temperatures of 40,000 degrees, this star is over 6 times hotter than the sun. But what's staggering is that Eta Carinae emits 1 million times more energy than our sun. If our sun was that hot, it would be 5 million times brighter than it is today. Violent ejections of plasma would scorch our planet regularly. And the sun would drench us in lethal amounts of UV radiation. There's no way you could survive the heat. If you stepped outside for just 1 second, it would be like stepping in an oven, only hotter. The blue sun would instantly burn all the tissues in your body to ashes and maybe even your bones. It would be game over for you. Just kidding, I wouldn't let you off the hook so easily. Okay, let's imagine that your body was super resistant to this extreme heat. there would still be that enormous amount of UV radiation to deal with. And it would wreak all kinds of havoc on your body, causing your skin to wrinkle, age, and get cancer. Your vision would suffer immensely too. You'd get something like a sunburn in your eyes. The UV radiation would make your vision blurry and your eyes would hurt like hell. It would be like snow blindness, except caused by the sun's radiation. In addition to losing your sight, the blue light would mess with your beauty sleep. Blue light suppresses your melatonin levels. With so much more blue light and so much less of this hormone, sleeping would be tough. Poor sleep could lead to high blood pressure, diabetes, and even heart failure. The blue light would affect a lot more than just us humans. Outdoor plants would grow smaller, thicker, and have darker leaves. High-intensity blue light would promote flowering in long-day plants that usually need at least 12 hours of sunshine a day to thrive. All the other plants that don't like as much sunlight would die. Well, you'd still likely have long-day garden vegetables like lettuce, spinach, and potatoes. But if our sun became as massive as Eta Carinae, you'd have heavier problems than what to eat in your new diet. The sun's new, incredibly intense gravitational pull would disrupt the solar system. Yeah, you'd see Earth and all the other planets get swallowed up by it. Instead of getting engulfed by this massive sun, you'd be lucky if Earth went a little sideways and got shot off into space. Then, we'd live on a rogue planet that's not held by a star's gravity and roaming in the universe. But we'd likely freeze up pretty quickly and die anyway. If there's one benefit, it's that all this chaos and destruction wouldn't last forever. Instead, it would end quite quickly. A star like Eta Carinae has a live fast, die young lifestyle. At its young age of about 3 million years, it's already nearing the end of its fuel supply. It could explode into a supernova sometime within the next 100,000 years. Our sun is about 4.5 billion years old, and scientists expect it to keep burning for another 7 billion years. So if we turned up the sun's heat, we'd be dooming our star and our planet to premature death. Not that many life forms would survive to see that day. The earliest life on our planet dates back to about 3.7 billion years ago. At that point, our sun was already 800 million years old. Back then, if the sun burned as hot and bright as Eta Carinae, it would have exploded as a supernova hundreds of millions of years before there was life anywhere nearby. So, our lives seem better with the sun burning at its current temperature. A black hole is on a collision course with our sun. And there's nothing left for you to do except sit back and watch the destruction of our entire solar system. How exactly would this epic collision unfold? How would this black hole end up in our planetary neighborhood? And what would it be like to witness all this from Earth? This is What If, and here's what would happen if the sun collided with a black hole. A black hole is not much different than any other object that has mass, except it's dense, really dense. All the matter it possesses is compressed to an infinitely small point at its center, called a singularity. Most black holes are the remnants of massive stars. And just like the stars they used to be, black holes have a strong gravitational pull. The more matter compressed into its singularity, the stronger the gravity. There could be as many as 40 quintillion black holes in the observable universe. Many are located at the centers of their galaxies, like Sagittarius A star, the closest known black hole to us. It resides right in the center of the Milky Way. But black holes could also go rogue. After an extreme event like a collision between two galaxies, a black hole can break free and start to wander. There could be 12 of these rogue black holes in our galaxy alone, and one could be headed toward the sun right now. If a wandering black hole were headed toward our solar system, it would first reach the Oort cloud. That's the sphere of icy objects surrounding the solar system, 2 light years away from us. As soon as a black hole came too close, the icy bodies in this region would be ejected from their orbits. You wouldn't be able to see the black hole for yourself until it reached the ice giants, Neptune and Uranus. Looking through a powerful telescope, you could see the gases being pulled away from these planets. All the gases and dust torn from Neptune and Uranus would form a region around the black hole known as an accretion disk. This superheated collection of gas and dust would orbit the black hole, making it visible. As it continued on its destructive path, you'd witness Jupiter and Saturn meet a similar fate. You'd be able to see with your own naked eye these gas giants disappearing from our night sky. Rocky inner planets like Mars, Venus, and Mercury would also be sucked into the black hole and destroyed into nothingness as you watched in horror. Only Earth would be spared. Not really, of course. I just wouldn't want you to miss out on your front row ticket to the destruction of the solar system. As the black hole approached our sun, you might think it would swallow it in one blazing gulp. No, instead, the strong gravitational pull would begin to pull matter from the sun, just like a strand being pulled from a ball of yarn. Huge portions of gas would be ripped away from it, and they would spin around the black hole, joining the accretion disk formed by the gas and dust of all our neighboring planets. This tearing apart of the sun would keep going until our star no longer existed. What's left behind would be nothing more than a gas cloud. Only the very end of the tail of this cloud might be able to escape the fate of being pulled into the black hole. As the sun's matter was being absorbed, lethal amounts of ultraviolet and X-ray radiation would be released in fiery explosions. This radiation would be hurled right in your direction, back on Earth. You wouldn't know the ultimate fate of the sun for 8 minutes. That's how long the light would take to reach us, but instead of the light source of our solar system disappearing entirely right away, the black hole itself could become extremely bright, possibly trillions of times brighter than the sun. And with the sun swallowed up, the stability of what's left in our solar system would be completely destroyed. An entirely new gravitational balance would need to be established. And in addition to all the lethal radiation raining down on Earth, extreme tidal forces would push and pull at the planet. This would cause massive earthquakes, volcanic eruptions, and tsunamis. Eventually, Earth would crack into pieces. Or maybe, in the best case scenario, unceremoniously ejected from the solar system. It's almost as old as the universe, and as massive as 34 billion suns. It eats stars for breakfast. And now it's about to consume ours. Behold, the great and powerful black hole with the catchy name J2157. If it came close enough to our solar system, how fast would it destroy us? How would it all go sideways for our sun? And how exactly would this monstrous black hole end all life on Earth? This is What If, and here's what would happen if a black hole swallowed the sun. Black holes are scary enough. They form when big stars explode in a supernova and then collapse in on themselves. The most common black holes, the stellar ones, are only 16 kilometers in diameter, but they have the mass of a star at least 10 times more massive than our sun crammed in them. All that mass compressed into such a small diameter makes black holes extremely dense. If you came too close to a black hole's vicinity, beyond its event horizon, its extreme gravitational pull would turn you into a spaghetti noodle. But there are black holes so massive that they make stellar black holes look feather light. These are called supermassive black holes. These monstrosities lurk at the centers of galaxies and take up space roughly the size of our solar system. But most of them don't even get close to the size of black hole J2157. J2157 is the fastest growing black hole in the known universe, and it's the second largest one. Its event horizon has a radius of 670 astronomical units, which is comparable to the distance between the Sun and Neptune multiplied by 22. Whoa! If that's not scary enough, J2157 holds the title of the hungriest black hole we know. To stay in good shape, it gobbles up matter at a rate of about 1 sun per day. Now, take this monstrosity and bring it closer to our solar system. You can imagine how that would play out. If J2157 could replace the supermassive black hole that sits at the center of our Milky Way galaxy, to us on Earth, it would look 10 times brighter than the full moon. That's because of its incredibly large accretion disk, the matter the black hole collected on its way to us. And because it always needs to be the center of attention. This monstrous black hole would outshine most of the stars in the sky. If a black hole under 100 million masses of our sun entered our solar system, it wouldn't swallow the sun in one go. It would gradually start pulling matter from our star until all that's left of it would be a cloud of gas. In that case, you could expect lethal amounts of cosmic radiation headed toward the Earth. But that's not how J2157 likes to deal with things. A black hole of that size and mass would devour the sun in a moment. But losing the sun would be the least of our problems. Our planet could be torn apart by the tidal forces from the black hole consuming our sun. Or it could be bombarded with an unthinkable amount of cosmic radiation. Or it would disappear into the black hole's event horizon, along with the rest of the solar system. Either way, you wouldn't get out of this alive.
What if, instead of shining brightly for another 5 billion years, the only star in our solar system turned into a dark and cold remnant, a black dwarf? How long would the Earth last without all the heat and light it gets from the sun? And how would the sun going dark change the universe? This is What If, and here's what would happen if our sun turned into a black dwarf. All stars have an expiration date. They don't just fade to black though. Stars like our Sun don't have enough mass to become a neutron star. They end up expanding to red giants and then shedding their outer layers until only their core remains. That's when they become white dwarfs. White dwarfs don't have fusion reactions fueling them up. They gradually cool down until one day they become black dwarfs. The thing is, there are no black dwarfs anywhere in the universe. Black dwarfs just haven't formed yet. You see, white dwarfs may not produce any energy, but they still have enough of it left to keep them shining, faintly, for hundreds of billions of years. Given that the universe is only 13.8 billion years old, even the oldest white dwarfs are still glowing at temperatures of a few thousand degrees Kelvin. In the case of our Sun, it will take another quadrillion years for it to cool down and become a black dwarf. That's 1 million years from now, give or take a few millions. Think humans will be around for that long? Well, let's switch it up. What if the Sun burnt out tomorrow? I hope you have a good supply of batteries on hand because the entire solar system would be thrown into darkness. Put on a few sweaters because it would become much colder too. Planetarily speaking, we're pretty spoiled here on Earth. With all the heat and light provided by the Sun, we're able to make a comfortable home on a rock hurtling through space at 110,000 kilometers per hour. It's easy to forget that we're just another speck in the universe. But if the Sun stopped burning, it would be immediately evident that we're just floating in space. After the first week without the Sun's heat, the Earth's surface temperature would drop to 0 degrees Celsius. After a year, it would go down even more, dropping to a freezing cold -100. That is, if the Sun turned into a black dwarf instantly, which is unlikely, even for our hypothetical scenario. Realistically, to become a black dwarf, the Sun would have to go through all stages of the stellar life cycle. From the main sequence star it is now, the Sun would expand into a red giant, fade out to a white dwarf state, and only then cool down to become a black dwarf. At the red giant stage, it would bake the Earth, most likely swallowing it completely along with Venus and Mercury. At least we wouldn't have to worry about freezing to death once the Sun shrank to a black dwarf. What about the rest of the planets, the ones lucky enough to have evaded the burning flames of the red giant? Well, they'd keep orbiting that remnant of the Sun as if nothing had happened. Even though the Sun would shrink to the size of the Earth, its mass would stay the same, meaning that its gravitational pull would remain unchanged. In the grand scale of the universe, the death of the Sun wouldn't change anything either. The Sun would be just another star to go dark, too small and insignificant to make the universe even a tiny bit darker. This is What If, and here's what would happen if the Sun exploded tomorrow. That star at the center of our solar system, that super hot ball of plasma that gives us heat and energy, and amazing complexions. Well, it's a ticking time bomb. The Sun is 4.5 billion years old, but it's only expected to last about another 5 billion years. After that, the Sun will expand, becoming a red giant. Then, it will shrink to become a white dwarf, a dying star, cooling for the next several billion years. Of course, we'll all be long gone before any of that happens, but still, can you imagine what it would be like to watch the Sun blow up before your very eyes? With a name like supernova, you'd think that a solar explosion would be the most magnificent fireworks show the world has ever seen. But in reality, you likely wouldn't see anything. The Sun is 150 million kilometers away from Earth, and it takes 8 minutes for light from the Sun to reach us. And while that may seem super far away, in supernova terms, we don't stand a chance. For Earth to be completely safe from a supernova, we'd need to be at least 50 to 100 light years away.
But the good news is that if the sun were to explode tomorrow, the resulting shockwave wouldn't be strong enough to destroy the whole Earth. Only the side facing the sun would boil away instantly. The lucky other half would experience a rise in temperature that would be 15 times hotter than the sun's current surface temperature. And permanent darkness. And without the sun's mass keeping us in orbit, Earth would likely start floating off into space, while its remaining inhabitants desperately struggle to stay alive. There is a chance that our planet could lock into orbit around another star that might provide the same light and heat as our sun, but by the time that happened, we'd all be long gone. If we knew in advance the day that the sun would explode, then we could buy ourselves as many as 1,000 years of time, provided we had the resources to sustain ourselves for that long. And we could. Just a few meters below the ground you walk on, the Earth is maintaining a temperature of about 17 degrees. So if we had enough time to prepare, civilization could continue to live by moving underground into a huge network of fortified bunkers. Within a week after the explosion, the surface temperature on Earth would drop to minus 18 degrees. Within a year, temperatures would plummet to about minus 73 degrees. At this point, the oceans would begin to freeze from the top down. Within 1,000 years, Earth's atmosphere would freeze and collapse, leaving anything left on the surface exposed to cosmic radiation and meteor impacts. Hopefully, by that point, we'd have found ourselves a new home. The good news is that if the sun were to explode, and it will eventually happen, it wouldn't happen overnight. When the sun does die, it will be a long, slow, arduous process taking place over billions of years. The sun will get hotter and brighter, and it will start to expand. During this process, it will lose its outer layers to the cosmos, leading to the creation of other stars and planets, in the same way that the violent burst of the Big Bang created Earth. Who knows? Maybe new life could form. Can you imagine another Earth? A new humanoid species? It's hard to predict how our galaxy might look billions of years from now, and it's especially hard to imagine our solar system without the great golden anchor that keeps us all together. But one day, in the very, very distant future, the sun will expand, and then it will shrink, maybe leaving room for a new star to take its place. And if by some miracle humanity still exists at that point, where might we be living?
What if the sun disappeared right now? Would you be able to handle eternal darkness? Cold temperatures? How about flying off into space? The sun is the only star in our solar system, and it gives life to everything here on Earth. Would we even be alive if it vanished? This is What If, and here's what would happen if the sun disappeared. The truth is, we wouldn't even notice for the first 8.5 minutes. This is how long it takes sunlight to travel to our planet. So even if the sun disappeared, its last ray of light would take 510 seconds to reach your skin. And what about gravity? The sun is the dominant gravitational force in our solar system. It has all 8 planets moving around it. So if the sun disappeared, would we fly off into space? Yes, but not right away. The force of gravity turns out to have speed too. In his theory of general relativity, Einstein proved that gravity is just as fast as light, and not instantaneous as was previously thought. This means the Earth would still be orbiting a recently vanished star with no clue of the upcoming darkness. But just for 8.5 minutes. When the last of the sun's rays reach the Earth, eternal night wouldn't be our only problem. The very same moment the sun disappeared from the sky, Earth would start traveling into space at 18 miles per second. Assuming the Earth didn't collide with any other planets or asteroids or get sucked into a black hole, it would be moving in a straight line for 43,000 years before it found another star to orbit. But you wouldn't have to worry about that. Within 2 seconds, the moon would go dark, since there would be no sunlight to reflect. But the stars would still shine, and your electricity would still work, unless it's powered by solar panels. However, gravity and illumination aren't the only things we rely on the sun for. Plants need the sun for photosynthesis. Turning light into energy is how plants stay alive. Without sunlight, most small plants would be dead within days. Larger ones, like trees, would survive for several decades due to their slow metabolism. This would knock out the bottom tier of the food chain. Most animals would die off slowly. Only scavengers feeding on the dead would remain until they froze to death. Because within a week, the average temperature on Earth would drop to a bone-chilling 32 degrees Fahrenheit. And by the end of the first year, minus 150 degrees would be the new norm. And it would keep dropping until stabilizing at minus 400 degrees Fahrenheit. The oceans would grow colder too, but just on the surface. Thanks to geothermal vents, they would remain liquid underneath, despite being buried under a thick layer of ice. So if you're lucky enough to survive, consider moving to the ocean floor. In the end, the organisms living around those geothermal vents would be the only living beings not to notice any difference. They don't need the sun to live and could continue to thrive for billions of years until the planet became a frozen chunk of rock drifting in space.
Ah, the sun! So bright, so hot. Time to jump into your super heat-resistant spaceship and get so close you could touch it. If you dare. How would you get to the sun's surface? What kind of temperatures would you encounter? And what kind of materials could even protect you from this scorching heat? This is What If, and here's what would happen if you touched the sun. Yow! The sun is so massive that it accounts for 99.8% of our solar system's total mass. With a diameter of 1.4 million kilometers, you could fit about 1 million Earths inside of it. It burns bright due to the process of nuclear fusion. Hydrogen atoms fuse to create helium, and it's worked that way for 4.5 billion years. It'll be another 5 billion years before it burns through all of its hydrogen. Then it will burn helium and will start to swell. Eventually, it will swallow Mercury, Venus, and the Earth. So you better touch it before it touches you. Okay, it's time to head off on your journey to the sun. Considering that big ball of gas has such a massive gravitational pull, it should be a pretty easy flight, right? Well, this journey is going to be more of an odyssey. That's because Earth is traveling almost entirely sideways relative to the sun, at a speed of about 108,000 kilometers per hour. To get to the sun, you'd need to cancel out that sideways motion. And that would require a lot of energy. About 55 times more energy than it takes to travel to Mars. Like the Parker Solar Probe, your Uber ship is capable of speeds reaching 163 kilometers per second. But you're still going to have plenty of time to prepare on the way. After 3 years, you'd arrive at the sun's outermost layer, the corona. This layer is located 7 to 10 million kilometers above the sun's surface. And big surprise, it's hot. About 1 million degrees Celsius. And that's about 900 times hotter than lava. At this point, you'd also be exposed to massive amounts of radiation. Make sure you slather on copious amounts of specially formulated sunscreen that could shield you from everything from ultraviolet light to gamma rays. Without this, you could get radiation sickness, leading to cancer, then death. Not the most ideal kind of sunbathing, right? Obviously, you should wear sunglasses too, or better yet, have a sun shield in your heat-resistant spacesuit. The sun would be tens of thousands of times brighter here than it was back on Earth. Traveling onward, you'd reach the chromosphere. Now you're 3,000 kilometers above the sun's surface. And surprisingly, temperatures here would take a big drop. In the chromosphere, they'd range from 3,700 to 7,700 degrees Celsius. And unlike other layers, it would get cooler as you get closer to the sun. But look out! Massive loops of plasma could jet out toward you. These are solar prominences, and they are extremely hot. Plus, they could be 10 times the diameter of Earth. You'd now see how granulated the surface of the sun looks up close. Below you would be bright expanses as wide as Texas, surrounded by narrow, darker regions. Next stop, the photosphere. You'd have finally arrived at the surface of the sun. As much as you'd like to land here, you couldn't. That's because the sun has no actual surface. It would be like stepping out onto a cloud, a scorching, searing cloud. The gravity would be so intense that if you weighed 70 kilograms back on Earth, you'd now weigh a whopping 1,800 kilograms. Outside of your ship, that extra weight would crush your bones and organs. Okay, pushing deeper from here, you'd enter the convective zone. Temperatures would now hit 2 million degrees Celsius. That would be almost 400 times hotter than Earth's core. The density here would be so intense, even light would have a hard time escaping. A little bit like in a black hole. You'd be cooking in a soup of densely packed solar particles, blinded by their luminosity. Finally, you'd make it to the core, 500,000 kilometers below the surface. This is where the sun's nuclear fusion occurs. Okay, so what would happen now if you reached out and tried to touch the sun? This would be light years beyond sizzling. You'd be almost instantly obliterated. A cremation furnace has temperatures of 1,000 degrees Celsius. That wouldn't even compare to the millions of degrees you'd encounter down here. And sorry to say, there's no material on Earth that could withstand these temperatures long enough for you to find out what the sun really feels like. The closest we could get right now is about 1.6 million kilometers away. Probably should have mentioned that at the start. What's the best place to put solar panels? Well, close to the sun, of course. And in this scenario, we're going to build the most efficient solar farm possible. And maybe, just maybe, that would make us a Type 2 civilization on the Kardashev scale. What would a sun-orbiting solar farm look like? How close to our star would we be able to put the panels? And how would we manage to get all that power back to Earth? This is What If, and here's what would happen if we put solar panels around the sun. Every second, the sun produces more energy than we humans have used in the history of humankind. And every 90 minutes, the Earth receives enough sunlight to power humanity for a full year. Only we're still far from gathering even a fraction of all that energy. In 2021, of all the electricity we generated, only 3.1% came from solar panels. Even if we built more solar farms here on Earth, not all of the sun's energy would reach us. Our star is radiating energy in all directions. And not all of the light that hits Earth even makes contact with our planet's surface. Some of it is reflected or absorbed by our atmosphere and clouds. Considering how much energy is lost before the sunlight even reaches the solar farms down on Earth, it would be much more efficient to get our solar panels somewhere they could face the sun 24 hours a day, every day.
Harnessing all the sun's energy could save you a lot of money, but is the risk worth the reward? Well, we won't know until we try, but not all investments are this way. There are many low-risk investments out there, but just one that I'm particularly excited about: contemporary art. Yeah, our sponsor, Masterworks, is the platform for investing in art by legends like Basquiat and Monet. They purchase financially attractive works they believe will appreciate in value for members to buy shares in. They purchase, you invest, they sell, and they know what they're doing. The 3 paintings they've sold have each returned over 30% net IRR to investors. Legally, I do have to add, past performance is no guarantee of future results, but 30%? That's incredible. Similarly, art prices have outpaced the Standard & Poor's Index 164% over the past 26 years, probably because these assets perform better during periods of inflation. I've always been interested in art, and now I get to invest in it, and for only a fraction of what billionaire collectors have paid. Skip the waitlist by visiting masterworks.art/whatif or click the link in the description below to start investing.
If you really wanted to maximize our solar power potential, you'd need to start with building a lot of panels. Solar panels are made of photovoltaic cells, or PV cells, that convert sunlight into electricity. And approximately 95% of the modules sold today are made of silicone. Unfortunately, you'd have to manufacture these cells on Earth before bringing your solar panels into space. And that transportation would cost a pretty penny. To save on expenses, you'd want to build your solar panels with the lightest materials possible. One idea would be to make your solar cells with lightweight gallium arsenide. With this material, you could build individual solar cells, each about the size of your dinner plate. Once you carried them into the Earth's orbit, you'd put them together in blocks as large as 60 square meters. That's about the size of 4 parking lots. With a good supply of solar panels, you could now start planning their arrangement around the sun. One model you could explore would be a Dyson sphere. That's a gigantic megastructure we could engineer around the sun. The scientist who came up with this idea actually stole it from aliens. He theorized that a much more advanced alien civilization built this hollow sphere around their star to gather all of its energy. So, if those theoretical aliens could rearrange their planetary neighborhood like that, well, we could do it too, right? Well, did I mention that this Dyson sphere would have to be gigantic? Yeah, the distance around the sun, or its circumference, is about 4.4 million kilometers. So we would need millions, if not billions, of individual solar panels to hug our sun. And our Dyson sphere would need to be a little further from the sun so that it wouldn't touch its scorching hot surface. Well, maybe instead of building such an impossibly massive structure, you could send a bunch of solar panels that would independently orbit the sun. And over time, more and more solar panels could be added to create larger, more complex structures. Surely there's no way the materials you used to build your solar panels could get anywhere near the sun without completely melting, right? Well, think again. NASA's Parker Solar Probe traveled through the sun's corona layer and heated up to 1,400 degrees Celsius. Impressive, but that's frigid compared to the temperature of the corona itself. It gets as toasty as millions of degrees in there. Yeah, you wouldn't be able to get that close to the sun unless humanity came up with lots of super heat-resistant materials. Forget about that, but you could build solar power stations a little further from the sun. maybe somewhere halfway between it and the Earth. You'd still be able to receive enormous amounts of power from there. Theoretically, if your space solar power station was 10 square kilometers, it could power 1.5 million homes. Compare that to Earth's surface, where you'd need about 6 million solar panels to generate the same amount of energy. Speaking of supplying Earth with power, how exactly would you manage to get all that energy back to our planet so we could use it? Well, your power transmission system would have to be wireless, and that would mean using microwave radiation. You'd need to build massive antennae. Your space solar farm would send microwaves back to Earth, and here, we'd turn them into electricity. These antennae would take up a lot of land, but they'd become your favorite scenic view. Of course, you could strengthen the microwave signal from your solar farm and use smaller antennae to catch it on Earth, but this would come at a higher risk. Microwave radiation could heat your body tissue the same way it heats food in a microwave. That means a strong enough microwave signal would cause painful burns. It could even cook you from the inside out. And not just you. Microwave radiation would roast anything containing water. Oceans, lakes, and rivers could start to boil. If water reservoirs below the Earth's crust heated up enough, the internal pressure could result in the whole planet exploding. But if you could get around these terrifying downsides, putting solar panels in space would be a huge advancement for our civilization. It could even be a step up on the Kardashev scale. This measures how advanced a civilization is based on the usable energy it can produce. Right now, we're ranked as a Type 0 civilization because we don't even collect all of the energy from our own planet. If we were able to harness all the power of the sun through a Dyson sphere or solar panels orbiting it, we'd jump up to a Type 2 civilization. That means we'd have more energy than we could even imagine right now. And interstellar travel beyond our solar system would become a real possibility. Something incredibly strange is happening. A mysterious gravitational disturbance is altering our solar system. Jupiter is now on a crash course with the Sun. What happens when one gas giant collides with an even more gigantic one? How would Jupiter journey to the center of the solar system? Would the Sun become even bigger and more powerful? And how might this be a life-threatening situation for us here on Earth? This is What If, and here's what would happen if the Sun swallowed Jupiter. Okay, before watching the greatest collision in our solar system's history, it'd be good to explore a couple of the ways this event could unfold in the first place. In order for Jupiter to crash into the Sun, something truly extraordinary would need to happen. Its orbit would need to be drastically altered by a gravitational disturbance. And not just any disturbance, an absolutely massive one. The most likely culprits would be a rogue star or a black hole passing dangerously close to our solar system. And these objects would have to be really huge. At the very least, they'd need to be a couple times more massive than our Sun. As they drift through interstellar space, they'd eventually interact with Jupiter's own gravitational field. And considering that Jupiter is about 318 times more massive than Earth, its gravitational field is an expansive one. And whether this rogue star or black hole tugs it in one direction or transfers a bunch of kinetic energy, it would make Jupiter's orbit increasingly eccentric. But there's a pretty big catch here, though. Somehow, those gigantic rogue objects would have to pass by at the exact right moment. A moment where they would only impact Jupiter. Otherwise, it wouldn't be the only planet in our neighborhood careening out of orbit and toward an imminent heat death. After a few billion years of orbiting the Sun at an average distance of 778 million kilometers, Jupiter would begin its death dive toward our star. But this wouldn't happen overnight. It could take years, decades, maybe even centuries. The gas giant would need to travel this incredibly vast distance, accelerating faster and faster under the immense pull of the Sun's gravity. This process is known as spiraling orbital decay, and it would result in Jupiter orbiting in tighter and tighter spirals until, well, it reaches oblivion. The next phase of this planetary destruction would occur when Jupiter would be close enough to be torn apart. This is known as the Roche limit, and for a body as big as Jupiter, it would begin when it's just under 900,000 kilometers from the Sun. At a distance this close, the planet would become tidally locked, just like Mercury is. This means that it would only make one full rotation on its axis for every full rotation around the star. But for that to occur before the planet starts to disintegrate, its rotation speeds would also need to undergo significant changes. Currently, Jupiter makes one full turn every 10 hours. But to become truly tidally locked at this distance, it would need to more than double its rotation speed. If this were to happen, only one side of Jupiter would ever fully face the Sun. And each of the two sides would experience varying levels of gravitational pull, with the day side or near side getting stretched out more and more. Jupiter would no longer resemble a gigantic gaseous sphere. Instead, it would have a more oblong, elliptical shape. You can almost imagine Jupiter going through the process of getting spaghettified, like what happens when an object crosses over the event horizon of a black hole. Though this would be slightly less extreme. But that doesn't mean it's not the end of days for our biggest neighbor. Its atmosphere would be getting stripped away, forming a glowing ring of dust and gas around the Sun. This is called an accretion disk. And this is where Jupiter's existential plunge would get really interesting. Both the planet and the Sun are mostly made up of hydrogen and helium. So, as Jupiter gets absorbed, would the Sun get bigger and more powerful? Well, considering that our planet is already warming at a dangerous pace, this could trigger some alarm bells for you. But don't worry too much. This collision isn't about to change much in terms of the Sun's energy output. As big as Jupiter is, it's only about 0.1% the mass of the Sun, so we're not talking about a hugely noticeable difference. For a short amount of time, the Sun would be a bit brighter as it converts all of Jupiter's energy. This would be the first effect that this whole scenario would have back here on Earth. You'd be treated to a little extra sunlight during the day, and the night sky would be a bit brighter as you watch Jupiter's final days before it vanishes into the Sun. The biggest effect would come from the gigantic gravitational hole that Jupiter would be leaving in our solar system. For billions of years, it acted as a so-called cosmic vacuum cleaner by attracting comets and asteroids of all shapes and sizes. Without its presence, Earth would find itself exposed to dangers in entirely new ways. The chances of impacts from large objects known as planet killers would become higher. And that would be one of the greatest existential risks for all life forms on our planet.
Oh my God! Oh dear! Are you filming? Yes, I'm filming!
In a couple billion years, our Sun will become so violently hot that it could wipe out all life in the Milky Way. But as it gets stronger, it could also help us live on places like Pluto and Saturn's moons. How can the center of our solar system be so giving, yet destructive at the same time? Well, in today's episode, we're going to go through the entire evolution of the Sun, from how it helped create life on Earth to how it could one day destroy us. One day old, 4.6 billion years ago, the first outlines of our solar system started to emerge. Seeds of new life sprung up from the remnants of older stars which had exploded. A huge cloud of dust, gas, and vapor emerged. This gaseous cloud began to collapse under the force of gravity and started to rotate. Then a dense core formed at the center. Meanwhile, the rest of the cloud had flattened into a disk that rotated around the central core. Smaller bits of dust and gas gathered together and began to form the start of our planets. The dense core began to heat up, glow, and exert pressure. This marked the birth of a protostar, kind of like the baby version of our sun. This was a ball made up mostly of hydrogen and helium. If you'd been around to see it, the protostar would have looked quite dark. Within the first 10 million years, the gas giants Jupiter, Saturn, Uranus, and Neptune were formed. Inside the protostar, the temperature and pressure kept growing. Finally, after 50 million years, something massive happened. The baby protostar reached pressures and temperatures high enough for nuclear fusion. Hydrogen atoms fused together to form helium. This gave off huge amounts of energy, and our sun was born. Then, over tens of millions of years, the rocky planets Mercury, Venus, Earth, and Mars were formed. Began its childhood. It was now burning 603 billion kilograms of gas every second. The energy given off in just this 1 second would power every household on Earth for the next 800,000 years. It's also incredibly hot. The surface temperature is 5,500 degrees Celsius, and the core could be as hot as 15 million degrees Celsius. The sun started off with enough hydrogen to keep it going for about 10 billion years, which makes it the single largest object in our solar system. 1.3 million Earths could fit inside here. If the sun had been smaller, then Earth would be in big trouble, like if it had become a brown dwarf star. This is a much smaller star that can never reach a core temperature high enough to ignite. Lucky for us, the sun was big enough to start powering nuclear fusion inside. This allowed it to radiate heat and energy, which helped Earth create and sustain life. Okay, we all know that the sun is incredibly hot, but let's dive a little bit deeper into what is happening with this massive star. In the sun's core, nuclear fusion reactions are going off constantly, the equivalent of 15 billion atom bombs every single second. So why doesn't the sun explode? Well, for every second of its existence, the sun is involved in a balancing act known as hydrostatic equilibrium. There are two forces at play here, each of which counter one another. Think of it as a tug-of-war between two equally matched teams. If each team pulls equally hard on the rope, it stays in one place. That's kind of what's going on in the sun. The strong gravitational force inside the core pulls inward, and this is offset by the massive energy from the nuclear fusion reactions, which push outward. These two forces balance each other out. Okay, at this point, our solar system has now completed its first full orbit around the center of the galaxy, or what we call one sun year, which lasts 230 million Earth years. Happy birthday to the sun. Sorry, I forgot to bring a cake, but it'd likely burn up or melt anyway. This young sun is only 70% as bright as our sun today. Think of this stage as the sun going through its emo teenage phase. No Riz. For the next 4.5 billion years or so, things continue at this steady pace. Because the sun is in a state of hydrostatic equilibrium, the nuclear fusion reactions continue without major changes. You might almost think this stage is kind of boring, but you'd be wrong, because there is one change which occurs very gradually, but it will be a big deal for all of us here on Earth in the future. It's the brightness. As the sun ages, it gets brighter. But why? the pressure increases. The increased pressure causes the sun to run at a higher temperature, increasing its brightness by about 1% every 100 million years. Now, 1% brighter every 100 million years might not seem like much, but over time it adds up. Remember, it's been up there for a few billion years. The other thing that's adding up is helium inside the core. Remember this, as it will be incredibly important later in the sun's journey. 4.6 billion years old. Okay, we're now in the modern day. The sun has reached middle age. Today's sun is 30% brighter than the young sun, and its nuclear fusion reactions are going strong. Now, with millions of these fusion reactions happening every second, will the sun never stop? Well, the sun only has so much hydrogen left, so the answer is, of course, yes, but luckily we have about 5 billion years left to go, so most of you won't see the sun die out in our lifetime. Now, if the sun was 10 times bigger, it would burn all its hydrogen much faster and die out sooner. A sun this size would have only burned for about 20 million years, and that's before any life was created on Earth. And if our sun was half the size, well, it would have been a red dwarf. And this type of star lasts anywhere from 80 to 100 billion years, but it's much more dim and significantly cooler than our star. So let's just enjoy the 10 billion years we have with our sun. All right, now that we've seen what's happening with the sun in the modern day, let's jump ahead to the future. 5.2 billion years old. Fast forward 600 million years into the future. The sun's luminosity has increased by about 6%, and that means the amount of solar radiation hitting Earth has increased, which is bad news for any life on Earth. Increased radiation causes carbon dioxide to leave the atmosphere, and this makes it nearly impossible for photosynthesis to occur. So plants will start to die off, and with plants gone, animal life will die out too. The only place life might be able to survive will be in the oceans. 5.6 billion years old. Okay, fast forward another 400 million years. The sun is now 10% brighter than it is today because the denser helium in the core is making the fusion run hotter. Earth will also be much, much warmer. It'll become a greenhouse, similar to Venus. Our oceans will evaporate, and as this is happening, the atmosphere will be saturated with water. This then splits into hydrogen and oxygen due to the heat from the sun, and the gases will escape, and the carbon cycle will come to an end. What was once a planet bustling with various ecosystems is now a lifeless rock. So what once gave us life is now the thing that's killing us. Let's just hope that humans have learned to live on other planets by this point. Maybe even other galaxies. Okay, 4.8 billion years in the future, the sun is now an angry old man trying to send back soup in a deli. It's 67% brighter than it is today, but just as angry old men do, it's slowly winding down. The hydrogen fuel in the core will slowly be running out as it transitions to its next phase. The layers outside the core will expand and cool, so the sun will become brighter and larger, but it'll still be relatively stable. If you stood on Earth and looked at the sun, it would be a bright red sphere and appear to be 1.5 times the size of the moon. But sorry, bad news, even if you were around, you wouldn't survive. Earth at 300 degrees Celsius will be like a pizza oven. A hard, dry rock, devoid of any water or any life, and it would be pretty much impossible to look at the sun. As the sun hits old age, it'll become a red giant. The hydrogen in its core is exhausted and helium has piled up. The sun's helium core has reached a mass of 140 Jupiters, and now it's at a breaking point. Core pressures and temperatures are incredibly high. This heat reaches the sun's shell, and hydrogen in the shell surrounding the core begins to burn. 500 million years later, the sun will be 34 times as luminous as it is today. And Earth will be hot. If you were to sail a ship on Earth's surface, you'd be riding waves of molten aluminum and copper. In another 85 million years, the sun will be 2,300 times as bright. Even your darkest sunglasses couldn't save your eyes. The enormous energy given off by the sun will cause its outer layers to expand. Earth will be reduced to its iron core, or it could be vaporized altogether. Now, the increased radiation from the sun might erode the atmospheres of Jupiter and Saturn, but there's a possibility Jupiter manages to survive. And there's another place that might suddenly become habitable. That's Saturn's moon Titan. With all the radiation from the sun melting its ice, it'll have liquid oceans of water ammonia, and might even feel like Earth. And Pluto, still not a planet, could turn into a tropical paradise. At this point, the sun is burning more nuclear fuel every 6 million years than it did during its entire 12 billion year lifespan, a phenomenon that's clearly unsustainable. Helium keeps piling up in the sun's core. The core now contracts, becomes super dense, pressurized, and hot. It's reached 100 million degrees Kelvin. Then, something astonishing happens. This is called, or will be called, the helium flash. This flash makes the sun's core exponentially hotter, and as this is happening, the sun will be brighter than all the stars in the Milky Way galaxy. But another weird thing is happening. The energy of the flash counters the extreme pressure inside the sun, so not much energy reaches the surface of the red giant. But everything that's going on transforms our sun. The core gets heated so intensely that it vaporizes, expands like crazy, and as a result, cools violently. In a quick 10,000 years, the red giant shrinks and dims to less than 2% of what it was. It's still 10 times the diameter of our current sun and 40 times more luminous, but compared to what it was, it's a mere shadow of itself, a subgiant. The sun is now an orangish yellow subgiant star. There's a feeling of déjà vu, as what happened with its hydrogen is now happening with its helium. Over the next 100 million years, the sun will burn helium at an incredibly fast rate, 100 times faster than it was burning hydrogen. As it's burning helium, the sun's core changes, becoming a carbon-oxygen core, 12.1 billion years old. Okay, finally, all the helium in the core has burned. Now the helium in the outer shell starts burning, and the sun becomes a red giant again, this time with a carbon core. But the carbon doesn't burn in a flash like helium did. Despite the high pressure in the sun's core, it's not high enough for carbon to fuse. The high temperatures in the core heat the outer layers, and they expand even further this time, beyond the orbit of Jupiter. The core gets very dense and becomes a white dwarf. Soon, the core and outer layers start to come apart violently. In a series of spectacular eruptions, the outer layers of the sun will split away from the core and be flung away, kind of like Marie Kondo decluttering the sun. Half of the outer layers will engulf the entire solar system and then disperse to become one with interstellar gas. The other half will be pulled into the dense white-hot core. It'd look like the sun was going from red to white. Now, if these violent eruptions all happened at once, the sun would lose mass and its gravity would weaken very quickly, allowing planets to escape into space. But this is no half-hour episode of Marie Kondo. This decluttering happens over millions of years, kind of like cleaning my garage. So, the remaining planets and objects from Jupiter to the Kuiper Belt stay bound to the sun, even though they're tied with a weaker gravitational force. Their orbits move further away. Now, you probably remember that Mercury and Venus got swallowed up by the sun in its first red giant phase. Earth too, but what about Mars? Well, based on scientists' calculations, Mars has a good chance of surviving both the first and second red giant phases. The sun's core will be extremely hot, around 170,000 degrees Kelvin, and it'll be about 4,000 times as bright as it is today. The energy radiating from the sun will light up the gases around it, creating a spectacular planetary nebula. But in just a few thousand years, this nebula will fade and die out. Okay, at this point, the sun is now a white dwarf. It's no bigger than Earth, but it's 200,000 times more dense. It'll spend billions of years cooling off. The oldest known white dwarfs from the stars born after the Big Bang have been cooling for 12 billion years, and they're still 5,000 degrees Kelvin. And whichever planets survive will orbit the white dwarf for billions of years more. But what if our sun were to cool down someday and finally become a black dwarf? Well, maybe in a few trillion years, but that sounds like a story for another What If. If our sun suddenly turned into a magnetar, we'd all be cooked, and pretty quickly. Magnetars pack about 1.5 times the mass of our sun into an incredibly small space. They're tiny and super dense remnants of ancient stars that have gone supernova, and they have an unimaginably powerful magnetic field. Yeah, this little star would kill everything on Earth, including you. In this video, we'll show you how life would change or end if we replaced our star with some of the most extreme objects in the universe. Some of these, surprisingly, could be better for us than the sun. But before we get into it, we want to hear what object you would want to replace the sun with. Why not tell us your pick in the comments below? Okay, now let's test them all out, starting with a red giant.
Oh my God!
Oh dear! Are you filming?
Yes, I'm filming!
The bad news is that the sun really will swell up into this kind of red and hot exploding star, and it would swallow Mercury, Venus, and even Earth. The good news is that it'll take 5 billion years to get there, give or take. You see, our sun is what scientists call a G-type yellow dwarf. It's a main sequence star. It runs on fusing hydrogen into helium, but its clock is ticking. The sun formed 4.6 billion years ago. A star like this only has a lifespan of 10 billion years. Only. And when it dies, it goes out with a boom. A red giant kind of boom. But we're not going to be around in 5 billion years to witness the death of the sun. So how about we speed things up and replace our star with the red giant now? Well, because that would mean instant death for you. Because as I mentioned earlier, this red giant would swallow Earth whole. You wouldn't even get a chance to enjoy the view. Immediately, Mercury, Venus, and Earth would be obliterated. And not because this red giant would be so scorching hot. No. The sun's surface burns at 5,772 Kelvin. That's about 5,500 degrees Celsius, or 10,000 degrees Fahrenheit. Red giants burn cooler, mostly because at this point in a star's life, it's burned up all of its hydrogen. This star's surface temperature would be around 3,000 Kelvin. That's just 2,700 Celsius or 4,900 Fahrenheit. But red giants got their name for a good reason. A giant reason, I should say. Yeah, this ball of helium would be 200 times larger than the sun. And it would be anywhere from 1,000 to 5,000 times more luminous. Even if you could look at it just for a second, you'd lose your eyesight. At first, everything would become very bright and orange. The sky would look like it's on fire. You'd be blasted by the most intense heat wave as temperatures on Earth rose by hundreds of degrees. Next, the oceans would boil and would disappear. Within minutes, Earth itself would get dragged into the red giant's outer atmosphere. Our planet's crust would melt. All life would burn. The red giant would reach Earth's orbit, blind us, broil us, and then there would be no more Earth left. Gone. Even Mars would get a violent blast of heat. Its carbon dioxide ice caps and permafrost would vaporize instantly, creating a thin atmosphere of gas and steam. It sounds like great news for Mars, but it's not really. Strong solar winds and intense radiation from the expanding red giant would strip away that thin atmosphere in no time. The Martian surface would be hotter than the melting point of lead. All the sand and rock on its surface would melt into a glassy blob. For a short time, Mars would glow like a red-hot coal, but then it would just end up as a dead rock.